Hi, welcome back to Act 2, and this is Lecture 10, High Algorithms. So Act 2 has been all about common tricks that we need to use for making our array programs play nice with JIT, just-in-time compilation. And in this lecture, we're going to bring it all together to implement a classical graph algorithm, Kruskal's algorithm, in a completely jittable way. This is going to involve a lot of branching and other sort of elements of computation that are going to be not obvious how to include in a jittable program. And this is going to allow us to discuss various performance trade-offs that come with different methods of working around the limitations against looping and branching in jittable programs. And so basically, let's just jump straight into it. We're finished with the JIT dojo from last time. And so we can just jump straight into, in the JAX repository, making sure I have the virtual environment active, I can go straight into lecture 10, where I have this environment script, which is going to be quite similar to what we built last time in lecture 9. And let me give you a tour of this and the differences, because we're going to make a few changes building on what we did last time. So basically, last time we had these same inputs, and we had this main function. I've changed the default size, which I'll explain later. And the code here actually in the main function is though the same. So we have a random key that we seed, and then we initialize an environment, which is this sort of environment with this static method init. And then we're going to render it. And then we're going to do some random walks. And the code here is for doing the random walks, a batch of random walks of length 512, 256 of the random walks. And it's going to do those in parallel using the walk function. That's the same as before. And then we're going to save the animation that we get, save as an animation the sort of results, the resulting trajectories that we get from that. The environment itself is going to have a few changes in how we initialize it and how we generate a random grid world. Because basically last time we were just putting random walls everywhere in the grid, but this time we want to do something a little bit more clever and use a graph algorithm to find basically a tree maze, which is going to have no cycles and it's going to have all walls. It's going to have lots of walls and it's going to have lots of structure. And so I've basically cleaned out the init method that we can sort of do some implementation of this graph algorithm and then come back and plug it in here, but we'll need to rewrite that part of the code. The rendering is all going to be the same. The step function is going to be identical, and the walk function is going to be identical, although I would like to make a change later. We'll come back to that. And then we have to fill in this section with the actual maze generation code, and that's going to be the main job today. And so this save animation is the same as last time. We don't need to worry about that either, but we'll just go ahead with this maze generation. We'll get started on that. Before we jump into actually writing the code, I want to explain the algorithm that we're going to use. So the algorithm is called Kruskal's algorithm, and I'm going to explain first how to use Kruskal's algorithm, how that finds a minimum spanning tree, and how we're going to go from a minimum spanning tree of a graph to a maze in our grid world environment. And then we'll implement that part of the code. And then I'll explain Kruskal's algorithm itself, and we'll implement it in a jittable way, which is going to be kind of non-obvious how to do that. But we'll be able to see how it all makes sense by the end. So let's get started talking about how to turn a spanning tree into a maze. So here on the board, I have an example of a grid world. And this grid world is just a 7x7 grid world. And it's going to be important for us that this is going to be an odd size. And that's why I've changed the size from 12 to 25, because it's going to be both a little bit bigger and it's also an odd number. Now, whenever we have an odd-sized grid world, then you could imagine that you can take every odd row and column position and consider that to be a node. And of course, we have already filled in here the border that we're going to have around the outside of our graph. I can then consider these odd positions. So this is row 1, column 1, and then row 1, column 3, and then so on. All 9 of the odd positions in the grid. I consider those to be the nodes of a graph, as in a classical graph like from computer science, where I would sort of take edges, all of the possible connections along a grid, where some of these edges are going to take over a different grid square. And now I've got this sort of 3x3 grid graph within my 7x7 grid. And now if I find a spanning tree of this graph, that would correspond to a tree. It should have no cycles, and it should have otherwise sort of the structure of a graph. It should be fully connected. Let me just pick a random spanning tree here. Maybe I'm going to include this edge, and this edge, and this edge, and this edge, and this edge. And then I shouldn't include this edge because that's going to create a cycle. And I shouldn't include this edge because that's going to create a cycle. Then I need to include a few more edges to include these nodes down here. So one thing I could do is I could just include this edge, and then this edge, and then maybe this edge as well. And then I'm going to have to get rid of these edges, and this edge, and this edge, and I've got a spanning tree. And it was randomly chosen. I just made it up as I went along. And so in order to turn this into a grid world that's a maze, what we can do is we can take all of the positions in the grid that weren't included as either nodes or edges in the grid, in this spanning tree, and also including the outside wall. And so that would be this position, 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 and this position. And I can add those all as walls. And then I've got what is starting to look like a maze, especially if I was to remove in green my spanning tree and say that those are the places that are going to have no walls. I'm kind of carving all of these out with my eraser. And now you can see we have left over what looks like a bit of a more interesting structured grid world environment for our hero to navigate. And so basically that's going to be the process that we're going to do. We're going to have an odd grid world. We're going to conceptually divide it into a grid graph and find a spanning tree. And then we're going to use that spanning tree to carve out a set of places where there are no walls that covers the world. And once we have this, we're going to be able to generate our environment by sort of generating one of these worlds, and then placing the agent and the goal in a random position, in fact, in a random junction, one of the initial 9 points that were at the odd positions for the columns and rows. We can just sort of randomly select one of these positions and place the agent or the hero there, and another one for the goal. And so let's get into coding that, and then we'll talk about later how we can use Kruskal's algorithm to actually find this random spanning tree. Okay, so yeah, first things first is we want to go to the maze generation part of the code and talk about what it would look like to actually generate this kind of Boolean grid with a spanning tree cut out of it like that. So I'm going to write a new function. I'm going to just make sure everything is jittered, but this is going to be a functools partial jit because I need this size to be static, obviously, because the result is going to have a shape that depends on this size parameter. So I want a functools partial jax.jit with static arg names equal to just the list with size. And then I'm going to define the actual function. I'm going to call it generate maze. So generating a maze is going to take as inputs a key, which is a PRNG key array. And then it's going to take this aforementioned size. And what's the return type going to be? I want it to be a Boolean array of size by size. And that is sort of what we expect. That's going to be the array that is true wherever there's a wall. And I want to make a note about size here that it's got to be greater than or equal to 3, and it has to be odd. And I'm not going to do any asserting or testing of that. I'm just going to sort of assume that we're going to be able to stick to that in the code. Now, in order to start carving out this spanning tree from this grid, I'm going to need to talk about this graph. And a graph is made up of nodes and edges. And so I want to represent those with some IDs conceptually. And so here's how I'm going to do that. So first of all, I'm going to sort of think about the 3x3 grid graph on the inside. And so I want to get a size parameter or a sort of an inner size parameter, which I'm going to call it capital S. and I'm going to set that equal to size over 2. And I'm going to say that that is going to be like corresponding to 3, for example, when I put 7 as the size as input. But if I put 25, then it would be divide and then round down, so it would be 12. And then I want to say that I'm going to have an array of node IDs, which is going to be JNP range of size squared. So where this is the capital S size, so the sort of inner size, the grid graph size. And so size squared, that represents the fact that we have 3 by 3 here, 9 nodes. And so this is going to be an array, in this case, from 0 to 8 inclusive. I also want to think sometimes of these nodes as an actual grid. So I'm going to say n grid is going to be equal to my nodes array dot reshape, and I want to reshape that to size. And so this is going to give me, for example, the 3 by 3 array in this case of 0, 1, 2, 3, 4, 5, 6, 7, 8. In 3 rows of 3 columns. And so this is just sort of like one conceptual representation that's going to be useful for generating the grid graph's edges. So I could call this whole section about grid graph nodes. And then I'm going to make a section called grid graph edges. Now, how can I generate these edges? Well, one thing you could do is you could divide this up into generating the horizontal edges and the vertical edges, which are going to be sort of, you can think about them a little bit differently. So for the horizontal edges, which I'll call H edges, one way you could generate these is by thinking, I'm going to use stack to get, so first of all, let me sort of say that I want to represent each edge as a pair of nodes. And so I need to identify the pairs of nodes that are adjacent to each other. And one way to do this is to sort of take these nodes all the way up to and not including the last column, and these nodes, and then sort of like associate those as if we were doing like a zip from the start to one away from the end, and then a zip including from one after the start all the way to the end. And so that's what I'm going to do with stack here. So I want to take all of the all of the right-hand side things of that, and that would be the n grid from all of the rows, but all the way up to but not including the last column. And I should probably flatten this because n grid has this sort of shape, but this will slice out everything except for the last column. And then I also want to stack this with n grid from the first column not included onwards, and also flatten that. And this will give me pairs of node IDs that are horizontally adjacent. And I can basically do the same thing for the vertical edges, but instead of talking about the columns, I want to talk about the rows, and so I'm going to sort of set it up like that. And that should give me all of the edges as, let me just be clear, the type of these things would be like then an int array, and let's say that there are, I guess it's going to be capital S times capital S minus 1, because we're taking out an S, a row of S things, or it's going to be S squared minus S, because we're taking out a column or a row each time. And so this will be S squared minus S, or if you call S squared n, because that's the number of nodes, this will be n minus S by 2. Because we've stacked, actually I guess that's the wrong way around, because when we stack it always adds at the start by default. So this will be a 2 by n minus S array, and this will also be a 2 by 2 by n minus S. And so what I could do is I could concatenate these together along the n minus S axis so that I had pairs of nodes with 2 times n minus S, or 2 times n minus 2 times S, if you like. And that would be my edges. So edges would be jnp.concatenate of these two things, h edges and v edges. And I need to make sure that I concatenate along the axis 1 or minus 1, like the last axis. And then actually, I'm probably going to be, it's more useful to me to have instead of 2 and then 2n minus s, it's probably more useful to me to have the 2 be sort of at the end. It just so happens. And so actually, you know, I'm not so sure about that. I guess I might try just leaving it here and see if we need to change it later. No, I do want the sort of the number of edges to be first. So I'm going to just transpose this. Transpose, and that means instead of 2n minus s, 2 and then 2n minus s, is going to be 2n minus s and then 2. And that means sort of the row dimension of this is going to be like which edge you're talking about. And then in the column is going to be like the first entry is going to be which is the first node in the edge. And then the next entry in the next column is going to be the second node in the edge. And these are going to be node IDs. Okay, so that's the grid graph edges. So now comes a little bit of magic that we're going to implement a little bit later, which is that I want to take, I want to actually do the algorithm for finding the minimum spanning tree, or I guess I should put this a little bit more descriptively, find minimum or find random spanning tree. So a minimum spanning tree would be if there were actually weights to the edges and you wanted to find like an efficient way of connecting all the nodes in a tree. But in our case, we're just going to think of the nodes as having, or the edges as having equal weights, and this is just about finding a random spanning tree out of all of the possible spanning trees. And so let me say that we have now included edges, or include edges, equals Kruskal, which is going to take our random key, because it's going to actually do some random choices. It's going to take our nodes, our node IDs, and our edges. And so this is basically going to be a function that takes an arbitrary graph represented as a list of node IDs and a list of edges which are in this format, and we'll implement this later. But for now, we can move on to imagining that we have include edges. But what is the shape of include edges? Okay, so I need to indicate that the shape of include edges is going to be the following. It's going to be an int array with n-1 and 2 as the dimensions. So how do I know that? How do I know there are going to be n-1 edges? And how do I know that statically? Doesn't it depend on maybe the randomness? Well, the thing is that with a spanning tree, it's always going to have the same number of edges actually, because any tree actually on n nodes that is fully connected is always going to have n-1 edges. And that's just a fact from graph theory. And so we can actually know statically, we can know that this will be an appropriate shape to have coming out of this function. And this will be a list effectively of edges that are still included. Now, if we have this list of included edges in this format where we have sort of like a number of edges, and then for each edge we have some node IDs, and we know roughly where the node IDs correspond to positions in the grid, then we should be able to now sort of like build this actual Boolean grid, but it's going to take a little bit more array manipulation. And so let's go ahead and do that. So let's start by building the grid and carving out these sort of junction points of these sort of odd points, junctions / nodes. And so we can start by saying, well, let's just make a grid that is fully covered with walls, and then we're going to take away where we know there's a node, and then later we're going to take away where we know there's also an edge that we decided to include. And so the grid, we can just start with JNP1s, and we should have a size by size grid. No, that's not right. It should be not S by S, but actually size and size, because this is going to be the 7 by 7, not the 3 by 3. And then we want to make sure that the D type of this is bool, so that it is like we expect a bool array, so we can it's the right sort of shape that we can return. And then I want to sort of set some of the values of this grid. So I'm going to do grid equals grid at, and then if I want to get all of the odd rows and odd column squares, then I want to take a 1 double slice to 2, or double colon to 2, and 1 double colon to 2. And what that means is this is stepping from 1 to the end of the array in terms of rows, and then stepping by 2, so taking every second one. And so that's going to be like 1, 3, 5, and so on, all of the odd positions. And then likewise for the columns, this will perfectly slice out this interior grid of junctions that I was talking about earlier. And what I want to do there is I want to set those to false. Because initially we have JNP1s, so everything is going to be true, everything is going to have a wall, and I want to make sure that there's no walls here where there are supposed to be nodes. So that is quite easy. And the edges are not going to be as easy, but they are going to be doable. So we're going to also carve out edges. And to do that, this is an example where it's a little bit tricky to do this if you want to keep this dimension of the edges along for the ride, but you can also notice that actually what we're doing is the same computation for each edge, and we could be doing this computation in parallel. So this is a perfect use of VMAP where it can save us a bit of a headache, my favorite feature of JAX. And so let me define what you would do if you had an individual edge as a pair, an integer pair, how you would operate on this array. Or actually, I'm just going to do the part where you would get the what would you do if you wanted to get the out the position in rows and columns to be able to index into this and set it to false. So let me say what is the edge pos that comes from a particular edge pair. And so an edge pair is going to be an int array of sort of length 2. And an edge pos is also going to be an int array of length 2. But these are going to have different meanings. So what the edge pair means is this is a pair of node IDs. So this is the format like 5, 6 or something like that, where that would be 0, 1, 2, 3, 4, 5. Okay, I guess it can't be 5, 6, but maybe it's 6, 7. And so 6, 7 would correspond to this edge. Whereas an edge pos is going to be what is the coordinate of this position in the overall grid. So let me see, that would be 0, 1, 2, 3, 4, 5, and then 0, 1, 2. So 5, 2. So 6, 7 would convert to 5, 2. And we're going to need to find out what calculation we need to do to make those conversions in general. And so in order to do that, once you have that idea, it's actually not so hard, and I bet you could come up with this. We've also done similar things in the past using divmod. And what we're basically going to do is convert the nodes to positions and then find the average, the integer average of those positions, which is going to be the appropriate, that's going to be exactly what we need. It's going to be the average of the positions of the nodes, because we always have this property that the edges are on either side surrounded by the node, either vertically or horizontally. And so that will work. So let's say we're going to use divmod on this edge pair. And we'll say the divs and the mods for each of the edges, for each of the nodes in the edge pair, is actually, I guess it's a little bit unclear to call this edge pair. Maybe it should be called node pair, but I think you guys get what I mean. We're going to say jnp.divmod of the edge pair, and the sort of modulus that we want to be working with is our s. And then this is going to wrap within the grid to get, actually, no, that's not right, is it? Do we want to use S or? No, okay, I think that is right, because these node IDs are in an capital S by capital S grid. And so this will give us the position in the node grid. Then we are going to have to map that to positions in the outer grid. And to do that, we're going to need to do basically this kind of slice. We're going to need to do the actual rows is equal to 1 plus 2 times these divs, and the cols is going to be 1 plus 2 times the mods. And what we've got here is a position inside the grid of like what row of the inner grid graph you're at, and then this is going to correspond to the row of the outer Boolean grid, and then likewise for the mods. So that seems good. Oh, and by the way, when I say plural here, it's because this edge pair has 2 values, and so this is for each of the nodes. So now I'm going to have rows and cols, which are going to have basically a pair of row indices. And so, for example, if it was a vertical edge, that would be like row, what would it be? So in this example, it would be row 3, row 5. And then in this example, it would be column 1. They would both be row 5, but it would be column 1, column 3. And so that's what rows and cols are going to generally look like. And so in order to convert those to the edge that is like the integer average of these ideas, we can just sum them and then take the floor division, because everything is going to be integers and everything is odd in this case. when we do the floor division, it's going to be the exact division, but as an integer, so that's perfect. And so that means that the actual row of the edge is going to be equal to the JNP equals JNP sum of the rows divided by 2, and the col of the edge is going to be JNP sum of the cols divided by 2, and that means we can have the actual position of the edge finally is equal to an array that combines both of those. So just the row and the col, and that is the type that we expected. Okay, so finally we've converted this kind of format of this edge as a pair of node IDs back into a row and column that is sort of indicating where the edge is in the graph, and that's where we can do the carve out. And so we can do this by using vmap, where we have this edge pos function, and we're going to vmap over all of the edge poses in the include edges. And so let me call this edge poses plural, and say jax.vmap of the edge pos function over the include edges. And then I'm going to take the grid and set at grid at the edge poses. I'm going to take all of the edges and go for the row, and then edge poses all of the edges and go for the column, and then I'm going to set that to false, and that will mean there's no wall there. And after I've done that, I should basically be able to just return the grid, and it should work. So all that's missing now is this actual Kruskal's algorithm. And so let's just take a moment before we go ahead and implement this. This is going to be a more complex part of the process. Let's take a moment to review Kruskal's algorithm and how it works. Specifically, not the full generality of Kruskal's algorithm for finding minimum spanning trees, but Kruskal's algorithm for finding random spanning trees is a bit simpler. So Kruskal's algorithm operates on an arbitrary graph that has edges. And in this case, we're going to imagine the grid graph, but I'm not going to draw it because I'm basically going to be considering whether I add edges or not. And so if all the edges have equal weight, you can find the random spanning tree by just considering them in a random order. So we're going to think of shuffling all of the edges in the graph and then considering them in just a random order. So I might pick a random edge like this one that we've been talking about. And I might say, okay, am I going to add that edge to the graph? And if so, is it going to create a cycle? Well, it looks like it's not going to create a cycle, so I'm going to go ahead and add it to the graph. And then I'm basically going to repeat that process, picking another random edge and adding it to the graph unless it would create a cycle. And if it would create a cycle, I skip and move on. So maybe another random edge I might consider is this one. And then I might consider this one. And then I might consider this one, and I would say, actually, that's going to create a cycle. So I won't add that, so I'll kind of cross that out and move on. And so Kruskal's algorithm is basically going to do that. And eventually, if you continue to do this, you are going to end up with a random spanning tree. And then maybe you consider here, and then here, and then maybe here, and then maybe you consider here, and that's fine. But then if you consider here, that's not fine. And the last one to consider would be here. But we don't add that, obviously, because that would create a cycle, sorry. And then we've got our spanning tree. So actually, how does Kruskal's algorithm do this internally? Well, we basically need some way to tell when I'm going to add an edge, is that going to create a cycle? And so I have to be able to look at the nodes on either side and tell if they're already in the same part of the tree and they're already connected or not. And in order to do that, the classic computer science solution is to have a data structure called a union find data structure. The find part of this data structure represents, we have a collection of sort of collections. We have a collection of groups of nodes, and I look at any particular node and find out what group it's in. Its group is going to have like a name or something like that. And I'm going to be able to find that name. So if I have two nodes and I can find the names of the groups they're in, and they're the same name, they're in the same group, and then I'm not going to add an edge. I'm going to skip that edge. Whereas if I find a pair of nodes that have different names for their groups, then I feel free to add them. But then here comes in the union part. So once I've combined the groups that the two nodes are in, I need to make sure that once I've added an edge, I need to make sure I combine the groups, because then next time when I look at one of these nodes, I need to know they're now in the same group. So I need to be able to take union operations between pairs of groups. And so there's a really clever way of doing this in computer science in classical sort of algorithms classes that you would learn, using a path compression kind of tree-based lookup that has like log star n complexity or something like this. It's very clever. It's very fun to learn about. But we're going to implement that first as basically a challenge, how to do this complex algorithmic computation with lots of branching in JAX. And so let me sort of prepare to do that. So here is our first implementation of Kruskal's algorithm. And I'm saying first because, spoiler alert, there's going to turn out a simpler and faster way to do it using the parallelism of GPUs, which was not really something that we would have considered in the sort of introductory computer science class when this came up. But in this context, it turns out to be better. So let's have this version of Kruskal's algorithm that I'm going to call Kruskal for now. And then let's say we have a PRNG key array, and then we're going to have the nodes, which is going to be some kind of int array with size n. That's going to be an arbitrary amount of nodes. And then we're going to have edges, which we said is going to be an int array with m by 2. We specified that was going to be the shape because we did that sort of transpose operation. And then we said that the output of this was going to be an int array of n minus 1, 2, because no matter what, as long as this graph is connected, the spanning tree is always going to have this n minus 1 edges in it. And so let's make sure that we are able to return that. And so the way that this union find data structure is going to work is for each node, we're going to keep track of basically a whole bunch of pointers to other nodes. And when those pointers get to a node that points to itself, we'll know that's the sort of captain of the group of nodes, and that's going to be the name of the group for the union find data structure. So initially, that means we're going to want to have this parent pointers all pointing to each node itself, because each node is going to be in its own group by itself at the start because there are no edges added yet. So I'm going to have this initial parents array be equal to the nodes itself. And then we want to consider these edges in a random order. So I basically want to use our randomness to shuffle the edges array. And so I'm going to do that. I'm going to say edges equals jax.random.permutation of, we're going to pass in the key and the edges and say axis equals 0. So let me sort of expand this out a little bit. And so with JAX random permutation, I need to pass in a key. This is the only randomness I'm going to use in the algorithm, actually. If I just shuffle up front and then consider the edges in a random order, that's equivalent to picking a random edge every time I need to pick a new edge. And so that's going to be enough. And the axis I want to shuffle on is this 0 axis, so this M. And then I forgot exactly what I need to call this. Maybe it's A or something like that, but I guess it couldn't hurt to just quickly check the documentation. And so let me have a look for permutation in the JAX random, and yeah, X is actually the name of the array. So let me fix that. Okay, and so now I have prepared my sort of parents array and my edges to be considered in a random order. I'm going to now proceed to the part of this code where I can actually try each edge, and then I'm going to scan this trying operation over all of the edges in this random array. So the actual operation where I'm going to try an edge and decide whether or not to include it is going to need to be looking like this. So I'm going to want a function called tryEdge, and this is going to be a function that I'm preparing for scan. So I'm going to think about what the carry is going to be, and what the input is going to be, and what the output is going to be. And the way I'm going to do this is I'm going to make the input the edge ID, or the edge as a pair of node IDs. And I'm going to make the carry this parents array that I'm going to carry through, and that's why I've got initial parents up here. And then I'm going to make the output whether or not I include this edge. So we're going to consider an edge, consider the kind of parents array that I've been accumulating all this time, And then I'm going to update the parents array and move it on if I might do some union operations. And I'm going to have whether or not this edge is actually included in the final graph be the output. So that kind of mirrors the computation that I was talking through when we were going through the example on the board. Let's see if we can implement that. So we have the parents as the carry, and we have the edge as the input. And then I said we're going to have the whether or not to include the edge as the output, but I'm not going to bother to write the type annotations for this scanned function. I'm just going to keep in mind that eventually I'm going to want to return the updated parents and whether or not to include this edge. So I'm going to call that a variable include edge. And so we'll work up to actually having those things defined. In the meantime, why don't we go ahead and actually start thinking about what this computation is going to involve? Well, first of all, I can take this edge and I can split it into actually some node IDs. So in classical graph theory fashion, I'm going to call these nodes U and V. And then I'm going to sort of do this find operation to recursively look up through the parents of a parents array and find out when I get to a node that points to itself, which indicates that I've found the name of this cluster. And so I'm going to say that RU, the root of U or the parent of U, and the updated parents array is equal to this find operation that I can run on U with the parents. And so this is like the starting point, and then I'm going to rip up through this parents array until I find this node. And the reason why I'm returning an updated parents array is because in the course of traversing up this sort of path through this tree that I'm going to build, where the nodes point to their parents, I'm going to reroute all of those nodes to point to the final answer so that next time I go up the tree, it's going to be a lot faster. And that is a standard trick that you can use from computer science that gives you the really good asymptotic complexity for this algorithm, because you make sure that you only sort of this tree of parents could get in principle very deep, but if you're kind of pulling it up every time you go through it, you're only going to deal with the depth like once, and then it's not actually going to affect the complexity that much. And so I can do the same for V, and I can sort of have another updated version of the parents, and I can talk about finding this V. And so let's, before we go any further, talk about what this actual find operation might look like. And so let me actually implement that. And so we can define find as, this is a little bit trickier. So we're going to have a node ID called X and a parents array. And then what I want to do is I basically want to do this algorithm that I sort of sketched in. I want to make my way up the parents array and then find when I get to the end what is the node that looks at itself. Initially, all of the nodes look at themselves, so this is going to happen on the first step. So the immediate parent of X is going to be parents of X, and then basically I want to do like a while loop or something like that. I want to kind of move my way up this tree until I get to the point where I'm definitely pointing at a node that points to itself. And so this is a little bit tricky, but if I was writing it in pure Python, it would be something like this. While x is not equal to px, then I want to say that the parent of the parent of x is equal to parents of px, and I want to then set x to px and px to ppx or something like that. And so this sort of steps both of these pointers up a level in the tree. But we're doing this with a while loop, and that's not going to scan, that's not going to JIT at all. So we would like this to JIT. So we're going to need to find a way to do this with a, we're going to need to find a way to do this in a sort of smarter way, using, let me just have a look at how I'm doing this in the solution. Yeah, I guess we're going to need to find a way to do this with a JAX while loop rather than a Python while loop. So let me sort of see. We can have the loop body function. We're getting complex here because there's an inner function, right? So let me call this find body function, and it's going to take some args, and it's just going to be sort of like a carry, I guess. And the carry is going to be, we're going to need to sort of keep track of this array, and then also keep track of the all of the we're going to need to keep track, think of this as an array, and then also we're going to have the parents array, which we're going to continually modify here, and we're going to have the x and the px, and I'm going to say these are the things that are stored in args. And so the find body function is going to be sort of like a carry style function, so it's going to need to return sort of an updated version of x, an updated version of px, and an updated version of parents, but we need to actually update those once we figure out what they should be. I guess we need to like look up the parent of x, which is going to be from parents of px, and then what I'm saying is that we want to, instead of considering x, we want to consider px, and instead of considering the parent of x, we want to consider its parent. And then instead of considering this parents, let's just reroute. This is actually, I think, a little bit simpler than the scheme I described, but it's a little bit easier to implement. We can update this x to point to its sort of grandparent, and that's like making some progress at least. Although it would be good if we eventually pointed this up all the way to the root. At least we're making some progress up, so this will probably have like not optimal complexity, but like pretty good. And then once we've got that body function, we should then be able to run the while loop, and the while loop is going to return the sort of final carry. So the final carry will be the parent of x will be the root of the cluster, and then the parent of that will also be the root, but we don't need to get it twice. And then the final parents array will be here, and that will be jax.lax.while loop. And so for a while loop, we need to provide a predicate, and we can just use lambda. Well, okay, maybe I need another predicate, but I want to do this. I want to do it this way. I want to say lambda args, and then if args 0, which is, remember, our x is being returned as like px, and then if that is equal to args 1, which is the parent of x, if x is equal to the parent of x, then we've kind of reached our termination condition. And in fact, I guess that means we want to continue until that is, we continue while that is not the case. And so this should be our predicate. And then we want this find the body function here to be find body function here to be the actual loop that we, the actual function that we iterate. And the initial carry should be just x, px, and parents. And then I think that is the while loop. And so what we should do now is we should make sure that we return the updated parents array we got out of this, and the root, which is the sort of root of above u. That is the thing that we eventually, that we sort of initially came here for. And all this stuff about modifying the parents was just to be a little bit clever and try and make this a little bit easier the next time we rip through this parents array. So let's return root and parents. Now this is like one of the most complex functions that we've probably written in this course so far. And if you didn't fully understand it, I wouldn't worry too much. I'm checking carefully to make sure that I'm not screwing anything up. And I think the lesson is going to be that basically all of the cleverness that we have here is not going to pay off because while loops are kind of expensive. And so this is actually, we're going to replace this with something much simpler in a little bit. Okay, but we can now continue with this try edge function. So we have, in principle, now found the sort of name of the group that our edge, each side of our edge is in, these nodes. And so we're going to decide whether or not to actually include the edge. And the condition for whether we include the edge is that these should be different. So we should be able to now write include edge is equal to, if RU is not equal to RV, then I want include edge to be true. And if they are equal, then I want it to be false. So these are just integers, so I can just compare them like this, and I get a Boolean. And that will be my include edge variable. So that's good. And then the next thing I need to do is is I need to sort of decide whether or not to union these. I need to decide whether or not to union these things in the parents array. And I'm going to run the union operation in the case where these things were not previously included in the same cluster. So if the include edge is true, then I want to replace parents with a version of the parents array that establishes that connection. And if the include edge is false, if the include edge is false, that means they must already be in the same cluster. So then I don't need to do anything. So let's see how we can do this. This is going to be another example of branching computation. And so what's the best way to do this? I guess we could, in principle, use JAX lax cond here because we're sort of dealing with like an individual case. But I want to sort of, I'm conscious that we're going to end up using, we're going to end up vmapping this and all sorts of things later. So, I don't think there's that much benefit to using cond. I think we should probably just use JNP where because it's going to make the code a lot clearer. So let's see the next parents array. The next parents array specifically is going to be equal to either JAX lax cond, JAX JNP where. If the edge was included, then I basically want to replace the parents array with a version where this link is established. And so one way I can do that is I can redirect the parent of at the root of one of the nodes to the root of the other. So what I know is from this find operation, I established that it must be the case that the root of u, when I put it into the parents array, is going to return the same thing itself. It's going to have a self loop. And so I could, for example, take that root of u and say, well, I want to put the parents array to point that root at the root of v. Let me see. So I guess I could say that if include edge is true, I want parents to be placed by parents dot at root u dot set root v. And then if parents is if the include edge is false and I'm not including any edge, then I think I don't need to make any update to the parents array. And so that should do the trick. In fact, it occurs to me that I might not need to use branching at all here, and I did in my solution that I prepared earlier, but just thinking about it now. How about this? So if we said that this include edge is false, what that's going to mean is that the root u and the root v are equal. And so what that means is if I do this, it's going to have no effect. And so why don't I just do that? Because then if it's false, it's going to have no effect. And I can just add a comment to say this is a no op if include edge is false. And then otherwise, it's obviously clearly an operation that is meaningful, but it's in the right way. So there we go. Let's do that. And so I guess I have to actually say parents equals this because it won't modify by itself. And then I'll just put this comment under here. And I think that's the try edge, and we've gotten away without actually writing a union helper function because this was so simple. So that's pretty nice. Now, once we've done define try edge, of course, we have to actually run this over the sequence of edges and then get the include edges out as an array. So that's going to require a little bit more work, but it's just going to be a scan. So we already talked about how we've prepared this function to be ready for scan because we've got a carry, which is this parents, which is being modified every single time we do the find operation, and also when we want to do a union operation. And then we've got the edge as the input. And so that's going to mean that the inputs into the scan is just going to be this array of edges that we've shuffled from up here. And then we have the outputs and the final carry, the sort of final parents. We don't need the final parents. Once we've done this operation, we don't need the parents array anymore. So let's put it like this. So final parents, which we don't need, we can put an underscore there to indicate that. And now we have an include edge mask, which is basically going to be an array of booleans. And for each thing in the shuffled array of edges, there's going to be a true if that edge was included and a false if it wasn't. So I'm going to call that include edge mask. And this is coming from jax.lax.scan. And that is going to be scanning, obviously, the try-edge function, which we set up to have the right shape for a scan. And then the initial carrier is going to be the initial parents, which we defined way up here as just the nodes themselves. And then the edges is going to be the inputs. And so if you like, it's kind of neat, I think, if we just have the nodes here. But I'm going to keep initial parents, because then it would be nodes edges. But initial parents is much clearer, I think. Okay, and so that's the scan. That's going to do it. Okay, so importantly, the include edge mask is going to be this Boolean array. So let me sort of say this here. Include edge mask is bool of shape m, where m was the number of edges, right? So that is important to know for what's coming next. So what's coming next is we actually have to return this n-1 array. And this is looking a little bit tricky because here we have a Boolean array. And we said we can't do Boolean indexing in JAX because normally that would involve changing the type depending on the values. However, we happen to know something that because this graph that we are going to supply here is always going to have the exact same number of edges, and in fact it's always going to be connected, and the spanning tree is always going to have the same number of edges no matter how many edges we even started with. Basically, we're going to be allowed to do a Boolean indexing here if we can tell JAX about all of this information, that we're going to sort of give it our guarantee that this is going to be fine and it's going to work out as the same shape every time. And so in order to do that, we basically have to use JNP where with the version where I said we don't normally use it. So let's have another look at JNP where. I wonder if this is going to work. Yep, JAX NumPy where. And so I want to use the version where we have size as an integer, and we don't provide the x and y thing. So we're not using this as like a branch. We're using this for Boolean indexing. But I'm just looking at the documentation here, and it says we should basically look at the non-zero command instead. Let's have a close look at that command and see what it tells us. So non-zero, because the size of the output of non-zero is data dependent, the function is not compatible with JIT and other transformations, and the JAX version adds an optional size argument which must be specified statically for JNP non-zero to be used with JAX's transformations. So this is basically similar to what we're going to want to do. We're going to sort of specify this size parameter that's going to make this work, basically. So if we specify the size, that's an optional static integer specifying the number of non-zero entries to return. If there are more non-zero entries, then they'll be truncated. And if there are fewer, then they'll be padded with this fill value, which defaults to 0. So that should be fine. We can basically do this in the case of where as well. And I just want to see what the return value will be. So if x and y are none, the function behaves differently. See JAX NumPy non-zero for description of the return type. I guess it's basically saying that it's actually going to return the return type from here, which is a tuple of JAX arrays of length a and dim containing the indices of each non-zero value. Okay, I think we could use non-zero or where. It seems like that is fine. So a tuple of JAX arrays of the right length that we want containing the indices of each non-zero value. So what we basically want to do is use this for Boolean indexing. So if we get a tuple of indices with this fixed length of size that we provide, then the computational graph stays predictable statically in terms of the shapes, because we know what size that is going to be, and we use that as an index into whatever array we like. So basically, we're going to do this. We're going to say the include edges, not the include edges mask, but the include edges, which is the thing that we actually need to return, is going to be edges, and then we're going to index in with something that is like a list of indices, basically. And this array index is going to go in and select a certain number of, like for example, I could just type, I want index 1, 2, 0, 2, and 4, or something like that. And that would just, that's sort of fine, because statically I know the shape of this that's going to come out is going to be 3 things, although I'm only indexing into the first thing here, so this is going to be a 3 by 2, because edges is m by 2. I want n minus 1 by 2. And so I'm going to need to have n minus 1 things here. And that means I'm going to need to use this where function, JNP where, and I'm going to use the include edge mask, and I'm going to need to specify, instead of an x and a y, a size equals n minus 1, which is known statically. I guess I should say not n minus 1. Do I have n? I actually only have nodes, so I need to say nodes.size instead of n. And then that is going to guarantee that JAX is going to guarantee that if there, let's say that I provided a mask here dynamically that didn't have enough booleans that were true, it's just going to put out some extra values. If I had too many that are true, it's only going to take a subset of them. So whatever, it's going to sort of make sure that this has size node size minus 1, and so the computational graph is going to be fine, and I'm the one who has to worry if I sort of don't do the right thing here. So this should work. Let's just see if it does. I'm thinking basically we should be able to run this code now, but I might have forgotten something. Oh yeah, of course, we have to set up the actual environment. So we've come a long way. We've implemented like quite a complex algorithm here, and there was quite a lot of work to get to that point even of sort of converting from the spanning tree in the graph sort of world into a grid world. And so now we have to sort of finish that by turning this into an environment that we can randomly generate. So in order to do that, we just have to take a look at another look at this init method and generate this random wall layout. And we're going to do that by, just like before, we're going to sort of split off a key, but this time, we're going to split off a key for the walls, but this time we're going to pass it to this generate maze function. That is going to give us basically exactly what we need in the shape that we need it. So we're going to say walls equals generate maze, and the key that we're going to give is going to be key walls, and the size that we give is going to be the size. So that's fine. And then we need to generate our random hero and goal positions. And so this needs a little bit more thought, but we already sort of discussed that we can just place these at junctions, and there's guaranteed to not be a wall there. So let's just choose 2 junctions. And so I can say key pos, like we did this last time kind of, but we placed them in random places on the interior. jax.random.split of our key again, so we get a new piece of randomness here. And then I'm going to say that indices are equal to jax.random.choice. Again, this is similar to last time, where key equals key pos. A equals size over 2, size over 2, so this is like a capital S squared, because that's how many junctions there are. Remembering that we have that many rows and that many columns that are odd. And then, actually I forgot a comma, so then we want 2 of these, shape equals 2 tuple, and then we want replace equals false, so that we don't put the hero and the goal on the same place. And then we're going to do our trick from before, our div, I guess I should call this divs and mods rather than div and mod actually, because there's multiple of them. But anyway, JNP div mod of indices. And this time I want to use size over 2 because I'm sort of taking these to, these are node IDs that I'm talking about. These indices, indices are node IDs. And so I'm going to use size over 2, which is our capital S, as the sort of width for the grid that I want to wrap to. And then the hero pos is going to be 1 plus 2 times JNP array div 0 mods, or divs 0 mods 0. I guess I'm doing this in a slightly different way than below, and that is more similar to what we did last time. But below I did a similar calculation with the edges, and maybe I'm realizing now that it could be cool to like factor out some helper functions for converting between node IDs, grid coordinates, and so on, that would sort of make this a little bit easier. But it's not that much code, we can just write it out. And I've already worked out the details, so we know what it's supposed to look like. Okay, so I think that should do it. And then we'll be able to take these hero pos and goal pos and make sure that those walls are free of walls. Actually, I guess we don't need that because we're guaranteed that they're free of walls by the invariant of the algorithm. And now we have another issue. So nodes is not defined initial parents. It definitely should be defined. I think that's just a typo here. There might be some more typos to work through. VMAP function must be passed at least one argument containing an array. That doesn't seem right. JAX.vmap of edge pos include edges. I think I probably just forgot to like return include edges or something like that, because it says it got empty args equals none and quargs equals. Okay, I think probably this is just a weird error that is saying that I forgot to return something. So let me just double check that include edges is actually getting returned from Kruskal's algorithm down here. We computed it, but we didn't indeed return it. So let's return include edges. And maybe there'll be a few more issues. Oh, no, okay. You know what? This looks actually pretty close, but there's obviously some issue. Actually, this is like pretty open-ended problem. So I might just pause the recording and then see if I can figure it out. Okay, I've narrowed down the bug enough that I'm confident that we can figure it out together. So, so this could be like quite instructive. So what I noticed is that it looks like the output of this include edges command, if I print this include edges.shape, is not what we expect. So let me just show that. Okay, so this is an issue. Oh, I think I've accidentally deleted too much. I accidentally deleted the wrong thing. Let me try that again. So print of include edges dot shape. And what gets printed here is 1 by 143 by 2. And what I actually wanted was so 143 corresponds to 12 by 12 minus 1. So that's what we expect. That's n minus 1 for a 25 by 25 grid. But we've had this extra 1 dimension here. And this is basically screwing up at the level of when we do the sum, it's sort of like pooling these things together instead of treating them separately, and we're ending up with a completely nonsense edge pos, and then we're not carving it out of the grid. So there must be a problem in the Kruskal algorithm right towards the end where the shapes aren't what we expect. So we need to be a little bit more careful there. And we need to basically make sure that this Kruskal's algorithm is going to return the right shape. And so that shouldn't be too hard because we can just sort of like print here and see what is the shape of this thing. And then we can make sure that we are doing this properly. I think, you know what, it might even be as simple as if I put that comma away, that might fix it. I'm not 100% sure why, so I would like to understand that. So why don't we just break this apart a little bit and say, say we have this jnp.where. Can I just print that out when I would compute it and see what it looks like? It looks like it's a JIT tracer int32 143. Okay, so we know that nodes.size minus 1 is 143. So this is a actually a tuple already of a single element containing an int array. And because this include edge mask is of one single dimension, it's this bool m, right? So I guess the where is going to be basically a tuple that is ready to be used for indexing. And so I didn't need to put an extra tuple. And by putting an extra comma here, I guess I've sort of implied that I want an extra dimension somehow in the sort of mysteries of edge indexing. Array indexing with arrays. So I think that pretty much solves it. Now we can move on. So we've got now coming out this. I'll better remove some of these print commands that were sort of just for debugging. We've got a very satisfying maze coming out. And this is what we were sort of looking for, is an environment that is much more challenging for the hero and involves a lot more structure. And we've generated this all with JIT because even though we didn't JIT the Kruskal's algorithm, we JITted the generate maze, which calls the Kruskal's algorithm. So Kruskal's algorithm also needs to be compiled for this to work at all. And so that's great. We've made a lot of progress here. But I would still like to see a simpler way of doing this that is going to save us some of this try edge and this while loop going on. And I would like to see, I would basically like to see also some animations of this. So let's go back to the start of the code where I've temporarily sort of said once you have printed this out you should stop, and then we can do the random walk. And so if I do the random walk, and it's actually going to go really fast and then save, I'm wondering if I'm even going to be able to see a difference in the performance of these algorithms at this scale, and I might not be able to, although I have profiled this these pair of algorithms in another context, this pair of implementations of Kruskal's algorithm. And so I do know we can get a performance enhancement by the simplification that I'm going to show. But anyway, we have now, in principle, we're going to have this animation. If I open output, we should be able to see here there's a big array of environments, 16 by 16 grid of these mazes. And if we look at an individual one, we can see the agent kind of struggling around the maze. This actually brings me to a topic that I'd like to discuss. I think this agent would make more progress looking around the maze if they were, or this hero, I should say, this hero would make much more progress if they didn't have to keep taking actions that led them to sort of just wait. That's sort of a useless action to just stand still. You should normally move because you've got a better chance of getting the goal that way. And also, if they ever take an action that pushes them against a wall, they're just going to not do anything. So that's also kind of a useless action. And so, you know, it's a little bit... we're not quite ready to be implementing a reinforcement learning algorithm that's going to teach this hero how to actually reliably navigate the maze and go to the goal. But it would be nice if we could sort of find just little tricks that we can use that will make their progress a little bit easier. And so that's basically my plan, is to just go to this other to-do that I had and basically rearrange this step function in the random walk to basically select from only among the valid actions at a particular point. And so we'll never consider the wait action valid, and then we will make also the other actions. Let me just find this random walk. We'll also never consider the we'll never consider an action that would take you into a wall to be valid. And so one way to do this is to this is a little bit tricky because the actions that are valid depends on what walls are around, which depends on the state, which, you know, this is like potentially a conditional computation. So we're going to need to figure out somehow a set of actions that's valid and then choose between those. And it's kind of hard to do that in a way that's statically kind of going to work, and it's going to work with JIT. But there's actually, it turns out, a pretty easy way to do this kind of screening of actions if we use random choice's probability feature. Because if we give an action 0 probability, then random choice isn't going to choose it unless there's a corner case where if all the actions have 0 probability, then random choice is going to sort of by default like choose one of them. So we have to watch out for that. But in this case, that won't be a problem because there always is at least one possible action that you can take in this kind of maze. Because you can never be in a situation where you're completely surrounded by walls, unless I suppose you're in like a 3x3 environment, and then we have bigger problems. Maybe we just need to make sure that our environments have some minimum size so that you can always definitely take at least one action. So what I want basically is to create a mask of valid actions, and I basically want to say the probability is going to be these valid actions. And if this mask is like of the 5, it's a 5-dimensional Boolean, and it's got a true when the action is valid and false when the action is not valid. I just need to compute that. And so I can do that, or like here, I can just say find valid steps. And I can say, in order to find if a step is valid, I just need to check that there's not a wall in that direction from the current position of the hero. And also, I need to make sure that the wait action is never valid. And so how can I do this? Well, one way I could do this is I could just sort of say, I want to probe into a bunch of positions and use these to index into the wall map. So I could say, here are my probes. I'm going to take the state which has a hero pos, and then I want to add to that an array of various different things that I'm going to use sort of with broadcasting. And so one of them is going to be, as you might guess, 0, 0. And then another one can be -1, and 0, and this is corresponding to moving up. And then another one is going to be 0, minus 1, corresponding to moving left. And then another one is going to be plus 1, 0, which corresponds to moving down. And another one is going to be 0 and plus 1, which corresponds to moving right. So all of these positions are going to give me like a bunch of positions that are like where the agent would be if we took this action. And so these probes I can use to figure out if there are walls around. So I can say it would get an invalid mask, or I get a valid mask, if I sort of take the state.walls and go for the probes in all of the positions of the probes array and get the corresponding rows, and then all of the positions of the probes array and get the corresponding column, and use that to index into the walls. Actually, this should be state.walls, not stat.walls. So that should tell me if there's a wall there. But if there's a wall there, I want that to be invalid, so I'm going to have to Boolean negate this array. And then I want to do one more thing, which is I want to make sure that this will never actually have a wall, but I do want to make sure that it's invalid. And so I want to say that valid equals valid.at0.set false, to make sure that the wait action is never valid. And now this should probably work a bit faster and better. So if I just do the random walks and then save, then this will generate a new version of this output GIF, and I can open that and have a look and see if our agent is, if our hero is making a little bit more progress to towards the goal. So it's just saving, open output GIF, and we can have a look. And it looks a little bit more fluid. It looks like it's not sort of standing still as much, and that is visually telling us that this hero is making a little bit more progress. Maybe this one is going to get the goal. They're pretty close, actually. Hey, there we go. And then we'll reset the maze. Okay, so that's pretty cool. So let me just close this again, and we can get back to talking about algorithms. So that was the last to-do that I had set out here, but of course there's more to be done, which is we want to sort of explore one more algorithm, one more way of implementing this Kruskal's algorithm. And so what I'm going to do is I'm going to call this this version of Kruskal's algorithm Kruskal Clever, because it's the kind of algorithm that you would learn in algorithms class in computer science degree. And then, I love this kind of class, and I really, for a long time, this was one of my favorite things to do. And I really actually enjoyed implementing this in JAX because it was very nostalgic. It was like, oh, I'm going back to my algorithms class where we learned this really cool algorithm. And it was a little bit tricky to put together, but, eventually it works. And I think I didn't quite do the full path compression, but it was good enough. And I was like, okay, I've done Kruskal's algorithm. And then I thought, well, hang on a second. There's a lot of while loops going on here. And if you want to vectorize over while loops, you kind of have to do the computations like almost as many times as the one that's going to take the longest. I sort of intuitively think that this is not going to be the most efficient way to handle things. And also, a lot of these operations are just modifying a single element of the array. When we have a lot of parallel computation available, it might be efficient just to modify a bunch of different things in parallel. Whereas if you were counting the number of modifications you made in algorithms class, that would be inefficient. So here's an idea for a brute force Kruskal's algorithm that I argue is going to be even more efficient. So let's call it Kruskal brute. And this algorithm is going to have, it's going to look very similar to Kruskal Clever. In fact, some of the code is going to be basically the same. I'm going to take the same type signatures and everything. I'm going to take the same initial parents and the edges code to generate the random permutation. And I'm even going to take the same scan almost. Maybe not. I'll double check that. But I'm definitely going to take the same include edges and the JNP where at the end. And I'm just going to change what's in the middle, how we compute this include edge mask, with a different version of the union find data structure. Actually, I think this try edges might even be the same. So let me just check that. And then we'll see how that goes. So let's just check this. So the thing that makes computing this find operation kind of complex and involving a lot of while loops is that we have this cheap union operation, And the cheap union operation, yeah, we are going to have to change this a little bit. The cheap union operation corresponds to basically saying, well, okay, once I set the root, I don't need to go back through the array and change the kind of label of all of these other nodes, because if they point to RU, then if I go with a while loop, I'm eventually going to get to the new sort of captain of the group, which is RV. This is sort of makes unioning very easy and cheap, but it makes finding a little bit more expensive. So the idea that I have in mind is to try and make instead unioning a little bit expensive so that finding is cheap, by basically saying every time we want to merge two clusters of nodes, I want to take all of the nodes in those clusters and set them all immediately to have the new label. And that is going to be the approach that we're going to use for Kruskal brute. And so let me have a look at this new version of the thing. If we just decided that what this parents mean was actually like immediately pointing to the root, and we just maintained that when we did our union operation, I think this would be really good. So let's talk about this try edge. So we're going to do the same thing where we sort of take the u and the v of the edge. And then we're going to sort of say, in order to find the RU, we don't need to worry about this parents, and we don't need to worry about some other find operation. We can just look at the parents and look at the U, and it should immediately point to the captain of that group, parents V. And we should just make sure that we preserve that property. And so if actually we can call this, rather than U, we can just call it P for parent, because it's the immediate parent. And then if we want to include an edge, it's still the same kind of computation. Whether we want to include an edge will depend on whether these things are in the same group, meaning they have the same parent. And initially, nothing will have the same parent because everything is its own parent, and that we have the same initial parents at the top. However, what we need to do now is a little bit more complex to figure out the new parents array. So the parents array now is going to need to update in a way where if we are not, we're going to need to go back to JNP where, I suppose. So if we're including the edge, then we need to merge these two groups, and we're going to need to come up with some parent array that merges the groups. And if we aren't, then we need to keep the original parents array because nothing needs to change. And so we need to sort of figure out what is going to go here. The thing that I think should go here is, oh, actually, I guess I've done something slightly different in the code, but let me just see about this. Yeah, basically we want to take the parents array and we want to say everywhere that the parent was PU, set it to be PV instead. So that is something we can also do with a bit of a branch. And we can sort of say, okay, I want to say JNP where parents equals PU. This is going to be a Boolean mask on the parents. And then where that's the case, then I want to say PV. And otherwise, I want to say parents. Should that work? Is it as simple as that? We'll find out. So we have this Kruskal brute. Let's try plugging it in to our maze generator, and we'll be using Kruskal brute. Still generated a maze. In fact, the same maze as we've been getting. So we seem to be like exactly the same computation that's actually going on in terms of randomness. Makes sense because we're using the same random key. Was it faster? That's a question. So I would actually like to kind of profile this. So why don't I just make sure that we're doing things in a way that is fair for the profiling, from a profiling perspective. By going up here and then just saying this jax.vmap and so on, I want to just make sure that this is block until ready. And I want to time it. So I want to, if I'm not importing time, I need to. Oh, I am importing time because I was doing some... so let's say start time equals time.perf counter, was it? And then end time equals time.perf counter. And then let's print elapsed time and then we'll take end time minus start time, and then that is seconds. And let's see how long it takes with brute. Okay, so block until ready is not how it goes, but I forgot what it was. Does anyone remember? I'm just going to have a quick look back in the overture. Lecture 0, ECA 1 should do it. And we had, no, I need to go to the one where I was doing compiling. So JIT, and then block until ready. It is block until ready. Okay, what have I done wrong? Environment has no attribute block until ready. Okay, well that makes sense because this is not an array, of course. I've never done block until ready on a pie tree. I guess that's the problem. So it is block until ready, but how am I going to make sure that we can actually block until ready? I guess maybe if I block until ready on one of the arrays inside the pie tree, that will probably be enough. And so I could just sort of, for example, take state BT and then look at the hero pos, which is one of the things that's changing so often, and then block that until ready, and then see if that is going to that's going to do the trick. Okay, so now this random walk looks like it's taking a little bit of time. So I think there was some laziness going on before. This is taking 5.68 seconds when we're using, and then saving is much faster than before. So I think this block on ready was actually an important step. In fact, I'm just going to be sure, I'm just going to make sure that all of the components, goal pos and also walls, are all blocked until ready. That seems like a good thing to check. So we're doing the random walks. We're blocking everything until it's ready. This is also involving the compiling, by the way, because we're just running this the first time. But I do want to include the compile speed, because that should not differ that much between the things. But anyway, it's taking 5.68 seconds roughly, so 5.7 seconds-ish. Let's see what happens. That was if we're using the Kruskal's brute. And let's see what happens if we switch to using Kruskal clever in our maze generator. So that was Kruskal brute. We can do a version of this with Kruskal clever. Okay, random walk. Hope it's not faster. Okay, seems like it's taking a little longer. 12 seconds. Okay, there you go. I'm sort of happy with that. Sort of a 2x speed up by being a little bit more clever in terms of doing things that are cheap on hardware that allows you to do things in parallel. This is just a CPU with, it's got however many cores the M2 has. It's I guess it's pretty beefy, but on GPU you might get even better benefits from parallelizing things. And so I guess the lesson to take away is just to think when you're writing an algorithm, think a little bit differently from in the classical kind of computer science class where you're thinking in terms of serial operations and counting the number of steps. Because things that you can do in parallel on GPUs are cheap, and things that you have to do kind of conditionally depending on like exactly what the inputs are, those are the expensive things. So while loops are generally expensive, especially when you want to have like a bunch of different of these parent tree traversals that depend on the specific values of the arrays that you're dealing with, and you're going to take like many different, very sort of different paths through these trees, and all of the cleverness that you end up getting there is sort of built for not quite the right model of what things actually cost when it comes to running things on GPUs. So just watch out for that. Anyway. Here is where I think we can leave it. I think we've done all of the things that I wanted to discuss today. So I'm going to leave you with the challenge and then sign off. And so the challenge that I wanted you to think about today is to try implementing some other classic algorithms and then jitting them. And so these are algorithms that I have implemented and I know it's possible to do, but there are various challenges you would have to go through to get them jitting, and it would be a good practice to do all of the things we've done in this act of hijacks. And so some algorithm suggestions are you could implement a depth first search or breadth first search, which is not super interesting on these grid graphs, with the tree mazes. But if you created a graph that had a grid world that had many more random edges, it might not be possible for the hero to even reach the goal. It would be interesting if you could come up with a function that could take a sort of Boolean layout and tell me, is it possible to reach the goal pos from the hero pos, or is there maybe a blockage in the way? And you could do that using depth first search or breadth first search, which are another two classic graph algorithms. Though in this case, instead of a grid graph, I guess you'd be working on the graph of the neighboring squares, which is another grid graph, but a different grid graph from the one that we embedded into the grids here at the sort of lower resolution. Okay, so that's breadth first search and depth first search is one option. Another option is if you wanted to actually find the shortest path between the hero pos and the goal pos and kind of solve this environment. And one thing you could do there is something like Dijkstra's algorithm. I haven't done that in JIT. I'm not sure how feasible it is. Another option would be to look at the Floyd-Warshall algorithm, which is algorithm for computing the shortest path between all pairs of nodes. Any two nodes, it will tell you what the shortest path is between them. And you can do a version that reconstructs the actual paths as well, or at least the directions that you would take from each node to get to any other node. And then you can actually maybe implement a version of this random walk. There's not a random walk at all, but a very directed walk where the hero just walks directly to the goal. So basically, can you solve arbitrary mazes? And this is like quite a challenging algorithm to implement in JAX in a way that's jittable, but it is something that can be done, and it would stretch your sort of JIT abilities and JAX abilities, and so I think this is a really good challenge if you want to take it on, with a very cool result that in the end you would be able to generate animations of the heroes solving these mazes as fast as possible, and that is pretty cool. So I'll leave you with that and sign off for today, and I'll see you in the next lecture. Bye!